Okay, welcome to our overview of chapters 12, 13, 14, and 15, where we'll explore the chemistry of Earth, air, water, and energy. In order to keep this a single semester course and still give a broad overview of general organic and biochemistry, we've had to make some tough choices, right? We didn't talk about chapter 10 on polymers at all, and we're going to have, unfortunately, very little time for each of these topics. That's not to say they're not important. Chapter 10 on polymers, as well as each of these chapters here, are among the most interesting aspects of chemistry, but they're also at a very general knowledge level, and they're items that I hope each of you will read on your own. If not now, then after the course is ended and before you do anything silly like sell your book back, definitely take a look at those. And certainly you can still email me questions or comments or anything like that. But in order to meet the learning objectives of the whole course, we will have to give a pretty cursory view to these chapters, not to say they're not important. And as I said, I hope you will go on to read each one in detail. Alright, so looking at chapter 12, Chemistry of the Earth, we're really looking at that main first part, the 12.1. We'll stop at the point where the text starts to talk about silicates in terms of what you're responsible for. But again, I encourage you to take a look. The silicates are very important, very exciting and interesting, and very close to my own research area that I was awarded my PhD in. So it's not that I don't like it or don't think you should like it. It's just that we don't have time for every detail of every topic. Okay, so in that 12.1, that first intro to the chapter, the main things that you'll need to know and be able to do are to describe the Earth's surface and the regions of the Earth's surface and their structures, and be able to list the most abundant elements in Earth's crust, at least the top 5. Numbers 1 and 2 are quite abundant, and then it starts to fall off, and we don't expect you to be able to list every element in the crust. Okay, so Spaceship Earth. Hopefully you've had a chance to go to Epcot and hear that term, but it is indeed a spaceship, right? It's an ideal place for us to be spiraling through space, or at least rotating through space. The Earth is divided into 3 main regions that you should have learned way back, probably in upper elementary school. The core is largely iron and nickel and is not accessible. We can't reach the core with current materials technologies. There's the inner core, which is solid, and the outer core, which is liquid, or at least we believe those to be the phases of the inner and outer core, and that's based on magnetic evidence, which is how we understand that iron and nickel must be largely the components of the Earth's core. The mantle consists of silicates and a variety of metals, not typically as metals, but as metal carbonates or sulfates or some other form. And then the crust is the outer shell of Earth, and we have the lithosphere is the land masses. The hydrosphere makes up the water bodies, and then the atmosphere is the air surrounding the Earth. So hopefully just a brief review for everyone, but if you haven't heard these terms before, it's been a long time. Make sure to do a little review before exam 3 comes up. Or I should say exam 4, sorry. And here we see a nice graphic. Again, if we could cut the Earth apart, this is what we would expect to find, and you see that solid metal inner core, again, ferromagnetic materials like iron and nickel based on the magnetic moments of the Earth, and then the molten outer core, then the mantle, and finally the Earth's crust, which is where we live, and it's very important to us, but obviously it's very thin. It's like the shell of an egg when we think about all those other regions. Okay. And here we see the elements in the Earth's surface, again, not considering the atmosphere. So don't think about the oxygen in the atmosphere. That's why nitrogen's not very high on this list, or even present on this list at all. But the oxygen we're talking about is the oxide minerals and other oxides like water and things that contain large amounts of oxygen here on the Earth's crust. So oxygen is king if we're looking at the mass percent. Then silicon's a close second, forming roughly between the two of them. about 75% of the elemental composition of Earth's surface by mass. Finally, we drop down quite a bit now with hydrogen in terms of mass percent, but a very large atom percent, because hydrogen's atomic number 1. It's a very light atom, so lots and lots of hydrogen atoms out there, but not a whole lot of mass due to hydrogen. And obviously water would be the main way that we would find hydrogen chemically bound on the Earth's surface in the hydrosphere. Then we go down to aluminum, and we go much lower to sodium in terms of atom percent, and then iron, which has a greater mass percent but lower atom percent than sodium. So things don't work out quite very nicely here, but mainly if you can keep oxygen and silicon straight, you're in pretty good shape. So the inorganic portion of the lithosphere is composed of rocks and minerals, and we see various oxide minerals, hematite, and magnetite, and corundum, oxides of iron and aluminum respectively. Then we have sulfides like galena and chalcopyrite, and finally the carbonates, for which calcite is the predominant carbonate, but lots of other carbonates exist. And we see some uses of them. Obviously magnetite, the name should clue you into the idea that it would have magnetic properties, ferromagnetism, and this would typically be the lodestone of the ships in the old days, where they could navigate by the magnetic North Pole of the Earth. And lots of other interesting uses. Corundum's a very hard oxide, so it's used in gemstones. Things like sapphire are mostly aluminum oxide. It's also used as abrasives like sandpapers, so on and so forth. So lots of great uses for these common non-silicate minerals. Obviously silica, silicon dioxide, silicate minerals are the primary, because we already said that silicon is the number 2 element in both atom percent and mass percent in the Earth's crust. Moving on to the organic portion of the lithosphere, again, chapter 9, our last chapter, organic chemistry, so hopefully that's a familiar term. That would include obviously the living organisms like us, things that are carbon-based, the waste from these living organisms and the decomposition products, as well as fossilized remains. So in particular, petroleum products were mostly fossilized, or high-pressure plant material that's converted over time into petroleum. So as we said in chapter 9, organic materials contain carbon, as well as elements such as hydrogen, oxygen, and nitrogen. So throughout history, at least human history, we've depended on our ability to extract materials from Earth that can sustain and enrich our lives. So obviously the pursuit of science and technology is the science end is devoted to the development of knowledge, and then the technology is devoted to using that knowledge and applying that knowledge for extracting and developing materials to enhance our existence. So obviously we're at quite a point now where we can consider things like hydraulic fracturing to free trapped gases, mostly methane gas, for natural gas exploration, offshore oil drilling. We've come quite a ways. However, we have to balance that with the knowledge that the fossil fuels will not be there forever, and we've got to start planning our next energy source, solar, wind, renewable sources that will be there as long as human existence will continue. And obviously once the sun burns out, we're gone anyways. We've either had to find someplace else as a species, or we have to say goodbye, because when solar is no longer feasible, living on Spaceship Earth is no longer feasible. Okay, moving into chapter 13, air. Air is an interesting substance. It's a mixture of gases, and for most of us, it's ignored. We don't even think about it. Fortunately, there's sufficient oxygen to support human life, but aside from maybe a gust of wind or a drafty winter day, if we don't feel the effects of air, we don't often consider it. It's invisible, it's odorless, it's colorless, but as we'll see, it's very, very important for our survival, and we are lucky to have an atmosphere that supports life as our Earth's atmosphere does. Some of the key learning objectives for this chapter include being able to list and describe the layers of the atmosphere and give the proportions, roughly the proportions of nitrogen, oxygen, argon, and carbon dioxide in Earth's atmosphere. Okay, so moving on to the layers of the atmosphere. Earth's atmosphere is typically divided into 4 regions. There's the troposphere, and that's the layer that we live on. It's the layer nearest Earth, and most living things live in this layer. The temperature decreases as you go up in altitude in the troposphere, and some examples of that would be things like mountains. Kilimanjaro, for instance, in Africa, quite a bit cooler up at the top of the mountain than down at sea level. The next layer is the stratosphere, and that lies above the troposphere and contains our ozone layer. Right, ozone is a great protector against ultraviolet radiation up in the stratosphere. It's very dangerous down at the troposphere. If we breathe in ozone, it can scar lung tissue. It's not good for living things to be exposed to large amounts of ozone for any length of time. But up in the stratosphere, the ozone layer is very helpful. Protects us from high energy ultraviolet radiation. We also have the feature that in this layer, temperature increases with increasing altitude, so opposite of what we see in the troposphere. There's next the mesosphere, and that's the layer that lies above the stratosphere. Obviously, troposphere lowest, then stratosphere, now mesosphere, and the last layer, thermosphere, is the layer above the mesosphere. So that's our layers of the regions, anyway, of Earth's atmosphere. And here's a nice image showing those different regions and also showing altitude and temperature. So as we said in the troposphere, as the altitude goes up, the temperature goes down. Then we have the opposite happening there in the stratosphere. As you increase altitude, especially as you near the top, the temperature starts to increase rapidly, and then starts to back off at the very top into the mesosphere, where the temperature goes down as the altitude goes up. And finally, the thermosphere, back like the stratosphere, has an increasing temperature with an increasing altitude. So, looking at the approximate composition of clean, dry air near sea level, we're overwhelmingly nitrogen, dinitrogen, right? One of those diatomic elements. So 2 nitrogen atoms with a triple bond together. So very, very stable substance. And that's about 78.08% of the atmosphere by volume, at least at sea level. The oxygen O2 at sea level is roughly 20.94% rather, and making up a total of over 98% of the volume if you consider oxygen and nitrogen at sea level. Again, this is not the upper layers where we'd have the ozone layer. We don't have any ozone essentially to consider down at sea level. Then we get into the much smaller components. Argon is a noble gas with a molar mass roughly that of the other components, a little heavier than air. Than nitrogen and oxygen, so it stays well suspended in the air at just under 1%. And carbon dioxide has been the subject of much discussion because of its increasing levels, but still, according to this table, which is a fairly recent table, about 0.04% by volume of carbon dioxide near sea level. Then finally, there's trace gases, which have very small amounts, less than 0.1% by volume. And you see those listed down below. So as we said on the previous slide, nitrogen accounts for about 78% of all gases in the atmosphere down at the troposphere. The animals and most plants can't use that nitrogen as N2 molecules. We rely on a few key organisms that can fix or use fixed nitrogen. And when we say fixed or to fix nitrogen, we mean that those nitrogen atoms from the N2 molecules can be, first of all, the bonds broken and new bonds formed to combine with atoms of other elements. So nitrogen fixing bacteria, for instance. Lightning can also fix nitrogen, as we see. Nitrogen and oxygen and the large amounts of energy provided by lightning can give rise to nitric oxide, and then the nitric oxide can react with further oxygen to form nitrogen dioxide, which can then go on to react with water to form nitric acid and additional nitric oxide, which can go through the whole cycle again. So that does contribute to fixed nitrogen in the oceans and soil, but as a strong acid, it also acidifies lakes and streams. Of course, this is small amounts, not large amounts of lightning striking any one region over a prolonged period. So it's a decrease in pH, but it's not nearly as substantial as what human activity does with sulfur oxides and nitrogen oxides from industry. The Haber-Bosch process is another way to fix nitrogen, and actually extended World War I by providing the Axis powers with a way to have cheap and available fertilizer. So before that, bat guano was used as fertilizer, and it needed to be shipped from Argentina to get to Germany, and the Allies cut off that trade route, and as cruel as it sounds, the goal was to starve out the Germans, but because Haber was able to develop this process in a useful industrial fashion, the Germans were able to continue to produce food, and the war dragged on even longer. But since wartime, we've made great use of this for civilian use to increase crop production, and it's given rise to the Green Revolution. Now we're trying to cut down on artificial fertilizers like those that Haber was able to create, but still important for sustaining the world population. I mentioned earlier about nitrogen fixing bacteria. Here we see certain plants called legumes contain bacteria in their roots that are able to fix nitrogen. And if you know the traditions of the Native American people who would have inhabited the Binghamton area, the Iroquois, they would have the three sisters, and they would cycle between corn and beans and wheat, I believe, would be the three sisters. And so that the beans were the critical ones. They were the ones that were fixing the nitrogen, but by going through that crop rotation cycle, you could have fertilizer nitrogen levels increased for the corn and the wheat, or whichever the third sister was. So indigenous people figured this out quite a while back, that legumes are quite important because of those nitrogen-fixing bacteria. Okay, moving into chapter 14, water. Water seems like such a mundane thing. It's everywhere. It's an everyday thing for us here on Earth. Water is one of the most unique substances in the universe. It does incredibly unique things, and you can't find a chemist out there who's not fascinated by water. It's just really amazing stuff. And will, again, just whet your appetite with a little bit of introduction to the surprising and interesting properties of water. So our learning outcomes for our brief foray into water will relate water's unique properties to its polarity and the hydrogen bonding of its molecules, and we'll also be able to explain how water on the surface of Earth acts to moderate daily temperature variations on Earth. Okay, so we see in these beautiful pictures some examples of water as ice, hexagonal ice. Water has a high density for a liquid and then expands when it freezes in most forms. There are forms of ice that don't occur naturally in most regions on Earth, but can be created artificially in the lab, that are indeed more dense than liquid water. They would not float on water like traditional ice, but they would sink. But the ice that we're most used to is hexagonal ice, which has this open structure due to the maximization of hydrogen bonding, and that causes that expansion. In order to get those hydrogen bonds in the ideal location, you make this hexagonal arrangement that has an openness to its structure, and therefore creates a less dense solid than liquid, which is quite unusual. It's not the only substance, but water is one of the few substances and one of the only naturally occurring substances that has that property for a liquid. So water's ability to hydrogen bond both with itself and with other substances are what make it so unique, and that hydrogen bonding with other substances is what makes it such a powerful solvent. It's considered the universal solvent. It doesn't quite dissolve everything, but it does dissolve quite a lot of different chemical compounds because of the hydrogen bonding ability. Water is also what we call amphoteric, or amphiprotic is another term for that, and that means it can be either an acid or a base depending on what it's interacting with. We see here an example where the two water molecules are just interacting with each other, and if you remember your Bronsted-Lowry acid-base language, we would have a proton donor and a proton acceptor. So the leftmost water molecule on the reactant side seems to be accepting a proton from the right-hand water molecule because it's becoming the hydronium ion, and then that's leaving the hydroxide ion as the co-product. So there we have water reacting with itself to form an acid and a base. Some other unique properties of water. In addition to that less dense solid than liquid that we mentioned, water has an incredibly high heat of vaporization for such a small molecule, for really any liquid for that matter. Since a large amount of heat is required to vaporize a small amount of water, it's commonly used as a heat sink. You can store a lot of heat energy in that water before it vaporizes. So oftentimes you'll see water used as what's referred to as a heat sink to absorb or retain large amounts of heat, depending on the application. If we want to quantify that high heat of vaporization or high heat of storage, we can look at what's called specific heat. Specific heat is the amount of energy necessary to raise the temperature of 1 gram of water by 1 degree Celsius. So this is looking at liquid water as a heat storage or heat release medium. And that 1 gram of water by 1 degree Celsius specific heat energy is quite high compared to anything else that's the size of water. Water is just a small molecule, H2O, 18.02-ish grams per mole, yet it has incredibly high specific heat and heat of vaporization and unique structural properties. So when we say that water has a high specific heat, well, if you look at this particular graph, the water's down there at the bottom, liquid water having 1.00 calories per gram degree Celsius, or since we favor the metric system in science, 4.184 joules per gram Kelvin. Kelvin unit is the same magnitude as the Celsius unit for a change in temperature, but obviously the absolute Kelvin scale and the Celsius temperature scale are not equal. They're offset by that 273 value. So looking at aluminum or copper, they're very, very small values compared to water. Really nothing on the graph approaches water even. The highest value we see there is the 0.561 calories, or 2.35 joules per gram degree Celsius, or Kelvin unit, of the ethylene glycol, and then ethanol is just slightly higher at 0.588 calories per gram degree Celsius, or 2.46 joules per gram Kelvin. But water's roughly twice the specific heat of either of those substances, and those, as you see by their chemical formulas, they're much larger in terms of molecular weight than water. So water is quite incredible, and hopefully you never think about water the same way after reading this chapter. Alright, so moving into the last of our topics for this overview, we have chapter 15 on energy. Obviously an important topic, and one that's been in the news for a long, long time. Energy is important to the modern life we enjoy, and we have to obviously consider how we're going to continue to enjoy such modern conveniences by finding new and different sources of energy. So the main objectives for this chapter will be to be able to perform power and energy calculations, and then to classify chemical reactions and physical processes as either exothermic or endothermic. All right, in terms of the energy that's available here on Earth, almost all of the energy that we have here on planet Earth comes to us from the sun, either directly or indirectly. So if we look at the energy in solar radiation, for instance, it's a huge number, just staggering, 174,000 terawatts. Obviously, if you know what a terabyte is, you know what a terawatt is in terms of that tera prefix, and that's huge. That's about 99.97% of Earth's energy is what's just freely available from the sun. The problem tends to be, of course, capturing that energy and storing it for later use. Internal heat, the heating up of the Earth by the sun, is still a sizable value here, 46 terawatts, but compared to that solar radiation, relatively small amounts. And then tides, as a result of the energy from the sun, as well as the action of the moon. Waste heat, that's again from fossil fuel use, that does cause some heat energy to be released. You've got the energy out. So of all that solar radiation, the 174,000 terawatts, about a little less than a third of it, 52,000 terawatts, are directly reflected right back into space. So we wasted almost a third of our free energy. That's good, actually, otherwise we would get far too warm as a planet, and life as we know it would be unsustainable. Then you've got direct heating, which is that solar radiation heating either the Earth, meaning the lithosphere, or the hydrosphere. Not a whole lot of heat stored in the atmosphere. We have the water cycle taking up a sizable amount of that energy, and then winds and photosynthesis, obviously quite important, but relatively smaller values of the energy out. All right, so when we mentioned the specific heat back in the chapter on water, we were talking about something that involved energy, right? We mentioned the joule specifically there. So energy is defined as the ability to do work or transfer heat, and the SI, the System International unit of energy, is the joule. So in science, we should always be using the joule. However, sometimes we still do perform calculations or list values in calories. Chemists in particular are notorious for that. The physicists are much better at sticking with the joule. But the calorie was around for so long and important to so much of the early work in chemical energy that it's still there sometimes. Notice it's the lower C calorie, so if you're talking about the food calorie, that's a capital C calorie, and that would be 1,000 times the lower C calorie. So for energy on food products here in the US, we tend to do capital C calorie, food calorie, whereas they tend to do kilojoules in the rest of the world. And then we have the SI unit of power is the watt, and a watt is a joule per second. So it's a rate of energy. That's what power is. Okay, looking at the big picture of energy, we can say that energy can be considered to exist in two forms. There's potential energy, which is the energy of position or stored energy. And then there's kinetic energy, which is the energy of motion. So here in chemistry, we tend to think about stored chemical potential, and then as chemical reactions occur, some of that stored chemical energy is released as kinetic energy, as heat, as movement of molecules. So looking at some exothermic and endothermic processes. So exothermic processes release heat, exo, to give off, and then endothermic processes absorb heat. So if you think about an exoskeleton, where the skeleton's on the outside, and an endoskeleton, like we as humans have, where the skeleton's on the inside, that hopefully will keep those exo-endo prefixes straight for you. So an exothermic process, believe it or not, is the freezing of water. It gives off some energy as that process occurs. There's also condensation of water vapor, which is why you would be better off to get burned by hot water than steam. The steam not only has a high temperature, but also will release a lot of heat on condensation. Metabolism in animals, that's a little easier to see as being an exothermic process, forming chemical bonds. Hopefully that's an obvious exothermic process for certain reactions. and discharging a battery is an exothermic process. If we think about the endothermic processes, those can be helpful, especially for those first couple. Like melting of ice, obviously that requires the input of energy from outside, and therefore freezing of water, being the opposite process, would be the opposite type of process. So if melting ice makes sense to be endothermic, then it shouldn't confuse us that freezing water would be an exothermic process. Same deal with the evaporation of water. It makes sense that that would be endothermic. The water requires energy to evaporate, so therefore the condensation of water vapor would be the opposite process. Photosynthesis in plants, the plants are capturing energy from the sun, and that's an endothermic process. Breaking of chemical bonds always requires the input of energy, despite what you might see in a biology textbook that has those starbursts around that ATP molecule. Breaking chemical bonds always requires energy. Making chemical bonds always releases energy. It's just the net overall that can be either endo or exothermic. And then finally, charging a battery is an endothermic process. You're absorbing that energy to get the battery back to its recharge state, and then discharging the battery will result in the release of that stored energy. So hopefully, if any of these processes didn't seem obvious as to why they're endo or exothermic, that's been cleared up a bit by us talking through them. Alright, so energy and the life support system. The biosphere is the thin film of air, water, and soil where life exists. Only a small amount of the energy entering the biosphere is used to support life, right? We only capture a little bit. As we mentioned before, most of the solar radiation is used in other ways. So 30% is reflected back to space, 23% powers the water cycle, which is an important temperature control system here on Earth. And then about less than 0.02% is used by green plants to power photosynthesis. So obviously it's a very important process, but overall it's not capturing much solar radiation at all. And photosynthesis, for those who don't recall, it produces oxygen and stores energy for all animals on the planet. So incredibly important, and just by capturing that little bit of energy through photosynthesis, we can support the entire biosphere, which is just incredible. Alright, so photosynthesis again produces oxygen and stores energy for all animals on the planet. The water cycle is important for temperature control, but if you are looking for oxygen for aerobic respiration and stored chemical energy for food for animals, then it's photosynthesis that is the driving force. So we see here the classic reaction. Hopefully you've seen that many times by now. 6 moles of carbon dioxide react with 6 moles of water, as well as the energy captured from the sun by chlorophyll molecules and various other xanthophylls and whatever we get to see when we have that beautiful color show in the fall to form glucose, a simple sugar, C6H12O6, as well as 6 moles of oxygen gas. Okay, an incredibly simple process, at least the overall reaction. If you wanted to see all the details, it gets quite difficult to follow quite quickly, but this nice simplified overall reaction explains the bulk of why we're able to live here on the Earth. We're able to live because of those photosynthetic plants and blue-green algae and whatever else the biologists tell us we need. Alright, so if we look at the factors that affect the rate of a chemical reaction, we have to consider these 3 main factors. So the temperature, increasing temperature increases the rate of chemical reactions. We already mentioned that's not true for nuclear reactions, but it is true for chemical reactions as a rule of thumb. Concentration of reactions, reaction rates are dependent on how much reactant is available. As concentration increases, rate tends to increase as well. And finally, the presence of any catalysts. So catalysts increase the rate of reactions by lowering the activation energy. So more reaction can get going in the presence of a catalyst than without the catalyst, because there's a lower energy path that becomes available. We also have to consider the arrangement of the reactants, the particular phase. If you think about a combustion reaction of sawdust, sawdust will burn very quickly compared with a log of wood. So that's another feature that isn't mentioned here, but does come into play for the rate of a chemical reaction. All right, so we mentioned it briefly on a table slide a few slides ago, but exothermic reactions release heat energy to the surroundings. So the burning of wood, for instance, is an example of an exothermic reaction. The stored chemical potential of the molecules in the wood give rise to the release of heat energy as they burn in the presence of oxygen, and we see you can even make some nice roasted marshmallows as a result of capturing that heat energy that the wood is releasing as a result of combustion. Endothermic reactions, on the other hand, absorb heat energy from the surroundings. So if we had a little bit of water, like we see here, and a chemical cold pack, a salt solution, for instance, as that salt and water as the salt solution dissolves in water, if you have a particular type of salt, even sodium chloride does it to a small extent, but ammonium chloride, for instance, does it very, very well. That little bit of water that you might have had underneath the Erlenmeyer flask and between the Erlenmeyer flask and the wood, it's often enough to freeze it. So that's how we can see that the reaction here, the physical process actually just dissolving, has an endothermic result where the Erlenmeyer flask is stuck now to the wood because the water that was in between them has frozen as a result of the Erlenmeyer flask contents absorbing heat energy from that water. So chemical cold packs are useful, particularly in athletics, where you need something to get nice and cold really fast. You just have those salts like ammonium chloride that can be quickly reacted or dissolved in water, I should say, and that will cause a rapid temperature decrease, and you get a nice cold pack very quickly. You also have chemical hot packs, as those hunters among us might know, where it's just a reaction that can quickly produce heat and oftentimes be able to be sustained for quite a while you're out there waiting for something to walk by. All right, and we see again that same table that we saw several slides ago, that table 15.2. Again, those same processes. Hopefully now it might make a little more sense since we've talked a bit more detail about exothermic and endothermic processes. As we begin to wind down our discussion of energy, again, hopefully just a taste to get you hooked on the chapter and reading more on your own, let's quote the First Law of Thermodynamics, which states that energy can be neither created nor destroyed. That's also known as the Law of Conservation of Energy, and much like the Law of Conservation of Mass, it no longer holds completely for reasons we talked about back in Chapter 11 on nuclear chemistry. We do have the ability to convert mass to energy, and that's Einstein's relationship, energy equals mass times the speed of light squared. So neither the law of conservation of energy nor the law of conservation of mass hold on their own, but together we do indeed have a law of conservation of mass energy. So fortunately we already understand that a bit, I hope, from the Einstein equation from chapter 11, but again, most of the time, at least for chemical processes, we do have law of conservation of mass and law of conservation of energy upheld. But when we do nuclear reactions, then we often see only the law of mass energy, the combined two, being upheld. And our second law of thermodynamics, energy flows spontaneously from hot objects to cooler objects. And we see our roasting marshmallows again, familiar image from a previous slide. And so that's just showing us that instead of the heat just retaining there by the wood, the heat flows from the hotter objects to the cooler objects until eventually a thermal equilibrium is reached. All right, and finally, along the same lines of the second law of thermodynamics, we have entropy, which is a measure of dispersal of energy. So another way of stating the second law is to say that for all spontaneous processes, the entropy of the universe is increasing. So we tend to go from more ordered states to more disordered states, or to be technically true from fewer possibility of states to a greater possibility of states. So hopefully that's enough the laws of thermodynamics to get you a little interested in energy and wanting to learn more. And hopefully for all the topics in the chapters we've discussed, that's the case. So we'll have to end there for now for this overview, but as I said, I encourage you, and I hope I've enticed you all to read each of those chapters in its entirety. Okay, and if you do have questions or comments, I'd love to hear them. So please do let me know, just because it may not be a particular topic that we were able to cover in this overview. I'd love to have the opportunity to communicate with you about that. Thank you very much.